Good evening, my fellow orbitologists. Those of you who find yourself within the astronomical persuasion may one day find yourself studying some new galaxy or distant object, and you'll find yourself wanting to know more about its history. And one of the best things you can do in that case is to determine its orbit. To get a grasp of the gravity of the situation, and to better understand galactic orbits, we're actually going to first examine orbit determination for individual stars in the Milky Way. Our two primary assumptions are that the galactic mass distribution of the Milky Way is symmetrical, both about the galactic plane and rotationally, and that close encounters between stars are so improbable that we can neglect them. Our coordinate system, shown in Figure 1, is cylindrical, meaning points are described using a radial component, an angle in the r-theta plane, which in the case of the Milky Way is measured in the direction of the galaxy's rotation from the Sun, and a z-component representing height above the galactic plane. The equations of motion for the orbit of a single star are shown here as derived from Lagrange's equations in generalized coordinates in the book Selected Exercises in Galactic Astronomy. To simplify matters, we assume that a given star lies in the galactic plane, i.e. has a z-value of 0. The gravitational force exerted on it, then, is described by the equation for Fr shown here and is a function of both radial distance from the galactic center and several parameters that characterize the rotational properties of the galaxy, known as the Oort constants. If you look at the equation for Fr, you'll notice that it looks similar to the orbital acceleration equation we're familiar with, where the central mass is treated as a point mass, but because the star is inside the galaxy, the gravitational force as a function of distance decreases more gradually than if the galaxy were simply a point mass, as seen in Figure 2. Compared to angles-only orbit determination of spacecraft, we actually have a couple advantages when working with stars. We're able to accurately determine the state vector directly using both angular position measurements over time and chemical knowledge of the target star. For nearby stars, distance is best determined using parallax measurements. To do this, you compare the angular location of a star relative to a distant stationary object 6 months apart, when the Earth is on opposite sides of the Sun. Comparing the angular location of a star against a much more distant stationary object is also used to calculate the proper motion of a star, which is its angular motion over time. Proper motion is best measured in intervals of exactly 1 year, so the Earth is at the same location relative to the Sun for each measurement, and thus parallax effects don't interfere with these measurements. These two properties are used to calculate tangential velocity of the star relative to the Sun. The remaining velocity component, radial velocity, may be measured by looking at the emission spectra of a star and comparing the wavelength of known spectral lines with their expected value. For example, if we're looking at a spectral type O star, we would expect the spectral line for ionized helium, which has a wavelength of 4,400 angstroms. If the spectral line for ionized helium in the star appears to be greater than 4,400 angstroms, we know it's traveling away from us and can compute the precise radial speed using a Doppler effect equation. Now that we know the target star's position and velocity relative to the Sun, we simply add those to the Sun's position and velocity relative to the center of the galaxy, and from there we can convert into cylindrical coordinates and integrate using the equations of motion to view the star's past or even predict its future. Now that we've examined star orbit determination, we're going to examine galactic orbit determination. And we'll look at 3 different cases: a satellite galaxy of the Milky Way, a neighboring large galaxy, and a distant galaxy cluster. For the first case, the Sagittarius dwarf spheroidal galaxy is a small galaxy in a very close polar orbit with the Milky Way, meaning it passes over the Milky Way's galactic poles. We can determine not only the dwarf galaxy's distance and velocity, using the techniques mentioned previously for individual stars, but also the motion of stars within the dwarf galaxy, which could themselves be modeled using a spherical form of the equations of motion for stars presented previously. In an actual simulation of the Milky Way and the Sagittarius dwarf galaxy, an n-body simulation similar to finite element analysis was used. Many particles, representing stars, were distributed in both galaxies according to their mass distributions, and each galaxy was divided up into a grid. In each grid space, the gravitational potential is calculated and used to calculate the forces on each particle. The results of this can be seen in Figure 3, where z refers to height above the galactic plane and y refers to lateral distance. And we notice that the Sagittarius dwarf galaxy is indeed in a polar orbit that takes it through the galactic plane of the Milky Way many times. Our next case study is the Andromeda Galaxy, the nearest large galaxy to the Milky Way. It's notable for having almost twice the diameter of the Milky Way and for being on a collision course with the Milky Way, with an ETA of 3.9 billion years from now. To determine the position and distance of the Andromeda Galaxy, parallax and proper motion against very distant stationary objects like quasars are still used, but these measurements are on the order of micro-arcseconds. These differences are so small that even on the best telescopes and cameras, they're on the order of 1/100th of 1 pixel. However, statistical data processing methods enable astronomers to obtain accurate measurements at high confidence, despite this. To propagate the positions and velocities of the two galaxies, an N-body simulation similar to the one used for the Sagittarius dwarf galaxy could be used. However, simply treating the two galaxies as point masses yields pretty accurate results for much less computation, at least until the two galaxies get close enough for tidal forces between the two to become significant. Figure 4 shows this collision modeled as a very simple one-dimensional linear motion between two point masses, and the time of collision using this model is calculated to be 3.88 billion years, which fits perfectly into the expected upper and lower bounds for the collision as predicted using much more advanced propagation. Our final case is for galaxy clusters. Most galaxies exist in very large structures with hundreds or thousands of other galaxies, known as galaxy clusters. But despite their name, only about 1% of their mass is actually represented by galaxies. About 9% of the mass is intergalactic gas, and the remaining 90% is dark matter, and as we'll see, dark matter drives the dynamics behind galaxy motion in these clusters. As before, to propagate an orbit, we must first find the initial state. Clusters can be very distant, making obtaining that state a problem. Parallax becomes less and less useful as distance increases, but redshift actually becomes an accurate measure of distance due to the cosmic expansion of the universe. This is because the expected redshift relative to an observer for an object at any point in the universe increases proportional to the distance from that observer. From redshift and proper motion relative to background quasars, the position and velocity of galaxies within a cluster may be calculated. Similar to the orbit of a star in the Milky Way, the gravitational field within an ideal spherical galaxy cluster is a function of radial distance and spherical mass distribution, which itself is a function of velocity dispersion parameters as seen in this slide. Now that we have the mass distribution and gravitational field for a galaxy cluster, we can examine the equations of motion for a galaxy within the cluster. For these equations to be valid, the cluster must have a spherically symmetric mass distribution and a smooth and uniform distribution of dark matter throughout the cluster. The first equation describes the acceleration experienced by any galaxy in the cluster as a function of the gravitational field, and a second term describing the drag force experienced by a galaxy as it moves through the background gas and dark matter particles. This drag term is a function of several additional parameters, including galaxy mass and velocity and background particle properties. For a galaxy orbiting closely to the cluster core, the motion can actually be described as that of a damped harmonic oscillator. This has some interesting consequences. The orbits of galaxies and cluster cores will decay due to the drag, similar to a satellite in low Earth orbit. Because decay time, which is equal to 2 tau, as shown above, is inversely proportional to galaxy mass, the most massive galaxies tend to have orbits that decay the quickest. And because the most massive galaxies tend to be the brightest galaxies, we can expect to see the brighter galaxies accumulating in the center of a cluster. And as more and more bright galaxies accumulate there, a single very bright superluminous galaxy will form. This is known as the cannibalism model, and has been observed in roughly 10% of galaxy-rich clusters. And that proportion will only increase as time goes on and more galaxy orbits decay. These clusters are one of the best examples of how knowledge of an object's orbit can greatly enhance the understanding of that object and its history. The orbital knowledge we've been applying to satellites and planets can, with a few mathematical modifications, be used to explain the motion of most objects in the universe, from stars to galaxies to asteroids the size of Texas on an impact trajectory with Earth. Hopefully, with these equations and MATLAB, you can now predict where anything is going to be however many billion years from now.